Hello everyone, so my name is Koji Nakabayashi from Kyushu University. I would like to talk about the title is Study on the Development of Carbon-Coated Alumina Support for Hydrodemetallization. In the current oil industry, demand of petroleum products is increasing with the global population growth. However, in the recent years, the production ratio of heavy oil in crude oil has been increasing. Along with this change, sulfur and metal components contained in crude oil are also increasing. Generally, crude oil is divided into these petroleum products. The heavy components are converted to high-value added products by residual oil cracking. However, metals cause deteriorating of catalysts and equipment for residual oil cracking. For this reason, hydrodemetallization has attracted much attention as pre-treatment. Typically, metals in crude oil are vanadium, nickel, and iron. As shown in the figure, the metal atoms are bound to the nitrogen atom and are confined to the porphyrin rings. Because the porphyrin rings are aggregated, it is usually difficult for the HDM catalyst to contact two metals. Aggregation of porphyrin is alleviated by hydrogenation. Consequently, the catalyst is able to contact two metals to remove them. HDM catalysts are used as such supported metal catalysts and supports. As shown in this figure, the sulfurized catalyst has multi-layer structure on alumina support. The edge of the layer structure is the HDM active site. However, there is a problem with catalysts. The problem is coke deposition on the alumina support during HDM reaction. The catalytic activity is reduced by the coke deposition. Therefore, it is necessary to develop a catalyst which can efficiently suppress the coke deposition on the catalyst. The objective of this study, shown here, first goal in this study, CA is prepared as support of HDM catalyst. By this, it is confirmed whether the carbon has effect of suppressed coke deposition. Next, carbon suitable for catalytic performance is investigated. We try to develop HDM catalysts with long life and high activity. In this presentation, I will talk about first goal. Here shows the rough experimental step. In step 1, CA was prepared by coating carbon on porous alumina. Nemo catalyst was supported on CA. In step 2, the prepared catalyst performance was evaluated by performance HDM reaction. Here shows the method of preparing CA. In this study, CA was prepared at each pyrolytic temperature. Prepared CA was analyzed by TGA and nitrogen, something like that. This figure shows the measurement result of TGA and the amount of coated carbon. The carbon coated amount increasing with the pyrolytic temperature. The carbon coated at higher temperatures showed high oxidation resistance. The figure shown is the appearance of each CA. The appearance of each CA was different. Next, this figure shows the result of nitrogen adsorption measurement of each catalytic support. Nitrogen adsorption amount was decreased with the carbon coating amount. The decreasing indicated an occurrence of pore blocking. Table 1 shows the pore structure of Ca estimated by method. For 600 Ca, the change of pore structure was not remarkable as compared with other Ca samples. From the results, we selected 600 Ca as the support for NEMO catalysts. NEMO supported Ca and NEMO supported as received alumina were used to compare HDM activity and carbon deposition rate to assess the effect of carbon coating on supported coke deposition. Here shows the method of preparing NEMO catalyst. The catalyst was prepared by the impregnation method using this reagent as the metal source. The reactive proportion of supported metal oxide as 2% and 8% on the weight of the support. This slide shows the HCM reactor and this table shows the respective reaction condition. In this study, we used AR as the target oil. The prepared catalyst was sulfurized prior to the HCM reaction. 3-cycle HCM reactions were performed using the HCM catalyst to investigate the cycle performance of the catalyst. Because of analytical difficulty of AR was fractionated into saturated aromatic resin and aspartame. Aspartame was used as to analyze the metal content because metal components are concentrated in aspartame. Aspartame and catalyst before and after the HCM reaction were analyzed. Aspartame was analyzed by ICP and the catalyst analyzed by TGA and nitrogen adsorption. The residual concentration of vanadium in aspartame before and after the HCM reaction were evaluated by ICP mass. After the HCM reactions, vanadium concentration decreased, and the reaction rate was larger for NEMO alumina. Next, here shows the result of coke deposition amount of the catalyst. The amount of coke deposited on NEMO Ca was less than that the NEMO alumina regardless of HDM reaction cycle numbers. This result indicated that carbon coating was effective to suppress the coke deposition on the catalyst during HDM reaction. Next, this figure shows the result of nitrogen adsorption measurement of each NEMO catalyst. For NEMO alumina, the nitrogen adsorption amount increasing insignificant from the first HCM reaction. For NEMO Ca, the amount of nitrogen adsorption gradually decreased with cycle numbers. The pore size distribution of each catalyst was estimated from nitrogen adsorption isosum. The result as shown in this figure. For NEMO alumina, the pore size rapidly decreased. On the other hand, for NEMO Ca, the pore size gradually decreased. For this result, NEMO Ca effectively supported the pore blocking by the coke deposition on the catalyst during the HCM reaction. This is a summary slide. Finally, I'd like to summarize the key point of this talk. NEMO Ca removed about 50% of vanadium in air. The carbon coating on alumina could effectively suppress the coke deposition by amount 4% on catalyst. Compared on NEMO alumina, the pore of NEMO Ca were gradually blocked by deposited coke in future plan, since the HDM reactivity of NEMO Ca was little lower as compared with NEMO alumina. The improvement of HDM activity in the next target of this study. Okay, thank you for the kindly attention.